All right, so we said that we were going to implement bigots for Wednesday. It's a good opening thing, right? So bigots, it's actually pronounced bidgets. Um, um, and that's this guy here, where we have we'll talk about that here in a minute. But this is where we're going for the question for Wednesday. So I think it's, where's the first question? And we're talking about environments today. Yeah, this guy. So 2.1 is what you'll implement for Wednesday's class. And I mentioned that on Friday, but didn't assign it over the weekend because we had a couple of people at the hackathon and they weren't going to have time to do any of this. So, that's this on page 34, this big num representation, and they reference it as sometimes being called a bidget. It's all the previous classes you've had with me, I've done all this number conversion crap, right? So, convert some number from base 10 to base 8, from base 8 to base 16, all this stuff. So a bidget representation has a base. So for instance, in this case, the base would be 16. Then the number 33 would be represented as a list of 1, 2, where 2 is in the ones place, 1 is in the 16s place, so on and so forth. 258 would be 1 in the ones place, 0 in the 16s place, 2 in the 256 place. So for 258, they do 2 times 16 to the 0. They're actually going, it's the other direction, I'm sorry. So it's actually backwards. So this one is 1 in the ones place, 2 in the 16s place. This one is 2 in the ones place, 0 in the 16s place, 1 in the 256 place. So it's what we usually think of as the number, but just reversed. So the least significant, it wouldn't be, the least significant bidget, let's go with that, would be in the far left, the car of the list. Does that make sense? So it's a list representation of a number of a certain base, where n is the base. So for 2.1, you're going to be implementing those 4 operations for bidgets, similar to what you did in the previous question, where we had those 4 different constructors, if you will. All right, so you'll write those for that guy, and that also we'll have, 0 is 0, successor and predecessor. You did this successor and predecessor before, didn't you? Or was that not in the assignment you did? All right, so then I was correct in saying similar to what you did in the previous assignment. So what they do up here is they talk about unary representation. So and that's kind of what this chapter is talking about is how do we represent data? So I want to kind of wrap this back to things that we've talked about previously. In other classes, I've talked about data representation languages, right? And what are our 2 popular data representation languages? This is an easy question. Give me one of them. What's one of the 2 popular data representation languages? JSON is one of them. What's the other one? What's the older one? JSON's kind of the newer kid. XML. JSON and XML. Anybody know where JSON comes from? For bonus points? Double Jeopardy? Is it Double Jeopardy? Is that a thing? Yeah, that's a thing. I don't know if it's related to this. You know what JSON stands for? What does it stand for? JavaScript Object Notation. So do you think it probably comes from JavaScript? So the way JavaScript represents their objects, the notation they use for their objects, is a JSON format. And when you think about what an object is in in any of the languages we've worked with before, it's effectively what? A collection of name value pairs, and then we expand, so that we call that fields in object-oriented lingo. So it's a collection of fields, constructors, and functions. Okay. Well, as we're kind of learning in here, if we say a constructor and a function are kind of the same thing, what have we learned in here as it relates to functions when we talk about functions compared to variables? Are functions a value type just like a integer literal is? And here we have defined a variable name and associated its value as being a lambda expression, correct? Is that a name value pair? That's a name value pair, just the value is a little scary, right? The value is this lambda thingy, which is our representation of a function in a language like Scheme. Does that make sense? So do you think that in other programming languages like JavaScript, C#, Objective-C, Java, whatever it is, do you think under the hood that the function type is probably just a data type that is associated with a name? There probably is some loopholes, right? Because those are strongly typed languages. So when you identify something as being of type, let's call it method or of type function, there's a little bit more assumed complexity there, especially if we want to start supporting things like recursion and things like that. But at the end of the day, if we're looking at it just at an abstract level, it's a name value pair. Here's the name of my function. Here's the value of it. It's something that takes some parameters and applies those parameters to some logic. Make sense? Okay. So there's no difference here. JSON is this object representation is at the end of the day is a collection of name value pairs where values can be all sorts of different things. Now the JSON language itself, that JSON representation, does not support the representation of functions specifically. It specifically supports our standard value types, strings, integers, chars, that kind of stuff, as well as the list type. So you can have square brackets, so think of that as like an array. And then it also supports another JSON object as a value type. So you can have a variable named blah, and its value can be a JSON object. Make sense? But it comes short of allowing us to represent functions. Why is that? Based on something, if we're trying to connect some of these dots, why do you think it doesn't support us writing functions? Is a language like JSON, is it a programming language? Why not? What do all programming languages provide us? What are the three things that every single programming language, 100% of the programming languages will give us facilities for? Okay, memory. Asking questions, so some sort of conditional type thing. What else? Come on, people. Repetition. I mean, this is something from freshman year, right? We've just been ingraining this stuff. I hate you all. But I kind of like Brendan. I got to know Brendan this way. I didn't really know Brendan before this. I didn't even know how to pronounce his last name, apparently. Like, you've seen his last name before, right? Linse. How do you pronounce that? Linz, you'd think, right? No, it's not how it's pronounced. Lindsay. Isn't that weird?
They do have a Lindsay in the family, too.
Yeah, really?
Yeah. She married him. It's not like someone's...
Oh, okay. It wasn't like the parents played just a horrible joke. Like, look what we're going to do to this kid. One of my friends growing up, his dad was a pastor at a Bible Baptist church or something like that. And so their last name was Burt, B-U-R-T. And they named the kid Robert Burt. Robert Burt. So whenever somebody had like call his name, it was like it became like a weird play on words. It's terrible. Apparently, I think in high school, my dad went to Overbrook High School in Philadelphia, which is not in the best part of town. And it's where Wilt Chamberlain went to high school. And he knew a guy in high school named Lewis. That's just lazy. Or drug induced, one of the two. Okay, write the name down here. It's just done. Okay, so what was the question I asked? That's something about. Oh, okay, so programming languages, right? Yeah, we came back. So programming languages. Every programming language gives us a facility for remembering stuff, asking questions, and repetition, right? Okay. Well, something like JSON, these data representation languages, their purpose is to give semantics to data, give meaning to data, represent data in such a way, or in some way. We already have a bunch of programming languages that allow us to operate on data. So the purpose of JSON or the purpose of XML is not to provide logic stuff. We can remember name value pairs. I mean, that's what JSON does. It remembers name value pairs. It represents name value pairs. We can't ask questions. We can't write functions. We don't have repetition. We don't have all the logic stuff built into the language because the language is meant to just store data with semantic information that describes what that data means. Make sense? So that doesn't mean it sucks. It just means it wasn't meant to be a programming language. It's still a language because it has a syntax and stuff like that, but it's not a programming language because it lacks those required elements. Okay? But in any case, so the connection we want to make here and that we've hopefully seen since the beginning of this semester is we're starting to treat what the book would call functions as first-class objects, where we can pass a function in as a parameter to another function just as easily as we can pass a number or a list or something like that. It's a type, right? It's a data type. We have numbers, we have lists, we have symbols, and we have lambdas. Those are just four of our options for types in this language, right? Just lambdas happen to be the unnamed representation of a function. And if we, kind of weighed an integer versus a function, we'd expect a function to be fatter, right? They seem to be more complex things, but at the end of the day, it's still just a value type. All right? So when we talk about data abstraction here, the idea we want to start thinking about really specifying data. We want to start thinking about this idea of how do we represent stuff almost like in a JSON-y type way. How do we say, this is the set of stuff I'm trying to represent. Here's some tools that allow me to work with that. But I'm understanding that the language that I'm using happens to let me store types that are kind of beyond the simple types. So these four functions that they're referencing in big integer, and I think they give us some examples of different types of unary representation. So like for instance, we all know the number system, right? 1 through 10, right? And there are... Everybody take out a piece of paper. Wednesday will be the alphabet. All right. Although you will have some college student that is so sleep deprived or something like that will come in and will miss letters in the alphabet. I guarantee it. Actually had an interesting conversation with my 10-year-old nephew because we were in Champaign this last week, and that's where my parents live. So I really did no work. Like I was at the hackathon for about, let's call it 6 hours, but most of that was like debugging the machines. I wrote no code. So these guys lost on their own. They didn't need me. They did a really good job. But the point is my family lives there. Usually I would participate more in the hackathons, but I was going out and hanging out with my dad, my brother, and my mom and stuff like that. Well, so we were at dinner, and my brother brought his two boys, and they were telling me about the stuff they're learning in school. I'm thinking, I'm pretty bright. I'm getting a little old, so I've kind of lost some stuff here, but I feel like I'm pretty bright. So you've seen the show, Are You Smarter Than a Fifth Grader, right? You've heard of it. There's truth to that. How much have we all forgotten? Isn't that like kind of a... So what he's working on, like I was telling him where the different people in the hack, he was asking me about the hackathon. I was telling him where some of the guys were from because we had some folks that aren't from the United States coming with us. And we had one guy, Joseph Muzo, who's actually from Nigeria. And was like, oh, do you know where Nigeria is? And so we had to, he couldn't come up with that. Well, is probably acceptable, right? In other words, I wanted to know if he knew what the continents were. And he had heard of the continents, but that wasn't what they were focusing on in school right now. So it's like he had trouble listing them. Like, oh, what kind of idiot is this? Blah, blah, blah. So what they're working on right now is the state capitals, the capital of every single state. Now, at some point in time, we all knew that, right? We had to memorize that for some test. Well, you were supposed to have known that, right? We were supposed to have known that. So he starts quizzing me on this. Now, in my defense, I feel like he got, let's call it 4.5 out of the 7 continents, right? Okay, I probably got 6 of the 50 state capitals, right? So I won that bet. But yeah, I mean, it's amazing. And at some point, I know for a fact I knew all of those. And then when he said it, I remembered. But I tend to think the state capital, I kind of know, oh, well, that's probably not the state capital, but the name I'm going to come up with is wherever their airport is, right? Must be in the state capital. Yeah, so I got very few of them right. It was quite demoralizing, actually. But yeah, so it's kind of amazing the stuff that we've forgotten. And then also at the same time, the stuff that we've remembered that's like useless information. Like at some point, I want to say it was maybe 7th grade or 8th grade, something like that. I had to memorize the Greek alphabet. How many of you have the Greek alphabet memorized? Well, so I think I might mispronounce a few of them, but that never fell out. Alpha, beta, gamma, delta, epsilon, zeta, eta, theta, iota, kappa, lambda, mu, nu, xi, omicron, pi, rho, sigma, tau, upsilon, phi, chi, psi, omega. Never fell out. And I have no idea why. I hit them all, right? Probably mispronounced a few of them, but isn't it the phi, it's actually phi or something like that?
There's no eyes, they're all
Yeah, phi, yeah. So did I say that right, phi?
Yeah.
Yeah, but whatever. I hit them all. I don't use that on a daily basis, but it just didn't fall out. Why is that?
Because it's so obscure, you feel the need to remember it.
You think you might be right. I don't know.
That's why I remember
It's almost like God has a really wicked sense of humor. Yeah, this guy's not going to know the state capital, the state he lives in. Okay, I got Madison right. Nailed that one. Okay, and of course, state capital of Illinois, Chicago. It's actually Springfield.
how often are you going to need to know the state capital of Maine?
Bangor, Maine, right? No, it's not Bangor, Maine. Bangor, Maine's the one you think of. It's no, it's lost again. But it's not. Huh?
Indianapolis?
No, that's Maryland.
I feel like I could do capitals of states with the states capitals too.
Oh, okay. So if somebody says the capital, you can say what state it is. Do you know what the capital of Maine was? It's not. It's something. I don't know. Whatever. But yeah, it's very weird how things just stay in. That's useless, and then things that might be useful. I feel like the state capitals might be more useful than the Greek alphabet in generalistic knowledge. I mean, you might benefit more from the Greek alphabet, in the direction you're going. But in general, and that doesn't come in all that handy, in everyday life. You're not, in the grocery store and it's just hitting, it's falling back in your Greek. Same thing with calculus, right?
Capital of Maine is
Augusta, yeah. It's always things you don't necessarily. I mean, we didn't even know there was an Augusta, Maine necessarily, right?
Yeah, when you hear Augusta, you think Georgia.
Georgia, yeah. Well, you're really thinking the Masters golf tournament. That's the only reason Augusta exists.
Yeah, that's small.
Okay, so back in. Now that we've covered our state capitals and the Greek alphabet, here's the 4 functions they're referring to there. So they want to have because we have different. Oh yeah, that's right. This started with how many of you know the number? The number system and the alphabet. Blah blah blah. That we went downhill from there. So we have a kind of an accepted representation of a number system, right? We use the decimal representation of the number system, where it's a base 10 base thing, right? And we, as we've kind of seen, as I've taught you the conversion stuff, we've kind of forgotten what that representation even means because we've kind of memorized it, right? But like if I tell you to convert from base 10 to base 10, you can go through the mechanisms of the conversion stuff one way or the other and make it work and see it work. So it's true, even though when you're using base 10, you don't have to think about that because you're very familiar with that representation. But what if you went to the grocery store and all prices were in octal? Or all prices were in hexadecimal? Something like that. Now, do you think that over some reasonable period of time you would get used to that, right? We would. If that was the new norm, we would get used to the alternative representation of our number system because they mean the same thing, right? I mean, we know that we can represent some value in octal and we can add 1 to that value or we can subtract 1 from that value. It's a mathable thing. I think that's an invented word, but we're going to count it. It's a mathable thing, right? But we've chosen decimal. And we can make our guess. It's probably even true that, 5 fingers, 5 toes. So, we can do the counting thing. Makes sense for us, okay? But we can all accept that there are various representations for numbers. We just happen to have chosen one of them. And outside of maybe convenience for us, just because of the way we're built, all those number systems are, relatively speaking, just as good as any of the other ones, right? They can pull off the same tasks. So in the decimal number system, if you were to represent a 0, the value that is 0, we write a 0. And that happens to be true in all of the number systems, right, that we're aware of. You probably can go back to some, ancient numbering systems where there was, it was just like how many sticks did you have there or something like that. But 0 is that's kind of an important base for us to have in all of our different numbering systems. Well, then we might want to say, is 0, is this representing the value of nothing? Fair enough. But now we have this function for successor and predecessor. Successor means which number comes next. So we can call it increment, but increment implies that we're changing the original value. Decrement implies we're changing the original value as well. So successor is what is the next value. So if we have 2, the successor of that guy is 3 in our number system. If we have 2, the predecessor of that guy is 1. Make sense? Seems very simple, correct? Even though it might seem kind of scary the way they kind of lay it out here. So if we have those 4 functions, we have a fairly functional numbering system. We know where it starts. We know how to tell to see if we're at the start. And if we know how to walk through the numbering system forwards and backwards, we've mostly described the representation as far as just the bare minimum. Is that a fair statement? Okay. So they give a couple of different representations here, I believe. So here's a unary representation. So the unary representation, the natural number n, is represented by a list of trues. So 5 would be a list of 5 trues. 6 would be a list of 6 trues, so on and so forth. Thus, 0 is represented by the empty list. No trues. 1 is represented by the list containing 1 true, so on and so forth. Make sense? So the productions for that guy would be 0 is the empty list. Some number plus 1 is the list containing a true followed by the representation of n. Some number of other trues appended together. Fair enough? Now, that's not a real great numbering system for us. It's not that efficient of a numbering system for us. If somebody wanted to, if you went to Best Buy and you were buying some piece of electronics that was, $1,600, you probably wouldn't want to look at a list of 1,600 trues and have to count through them as 1, 2, 3, 4, 5. Not efficient for us, but not inaccurate. Right? Okay, so we're going to call this a reasonable representation for numbers. Fair enough. All right. And then they say, so here are your those 4 functions. Here are how those functions can play out if you are writing those 4 functions as a representation of the unary set. 0 says, are we looking? So the 0 function is a lambda that takes in no parameters and returns the empty list. That is the representation of 0 in the unary representation. It's the empty list. That's 0. Is 0 is going to be a lambda that takes in a number, a unary representation, and returns true if that thing is the empty list. False otherwise. Successor says, I'm going to take in a list. I'm just going to const true onto the front of it. Predecessor says, I'm going to take in a list. I'm just going to return the cooter of the list. Everything but the first element. That's one less than it used to be. What's the benefit here of the unary representation from an implementation perspective? Pretty simple. So now when we look at it this way, the unary representation, since we've gotten pretty good at manipulating lists now, this is a pretty trivial implementation, right? What was the real hard part of getting to this point? Kind of even understanding what they're asking, right? Kind of dumbing it down and saying, okay, well, they're talking in all this high speech. But what they're actually just talking about here is lists of truths and falses for representing things, which we can all wrap our minds around after you finish reading through the stereo instructions. Now we have our scheme number system. Well, scheme number system is our number system, right? It's a reasonable representation because who's the user of the scheme programming language? Humans. And we like the whole base 10 number system, so they've kind of provided us with the mechanisms for meeting us where we are. You know, that's the whole purpose of programming language. That's the idea of those high-level languages, is that we're not equipped to do the 0 and 1 binary stuff, right, with the 2-button keyboard. We're not equipped to talk directly to the hardware, you know. So we asked the programming language to come 95% of the way to us and let us solve problems in the way that we're already used to solving problems so that we only have to kind of learn the skill set of breaking things down into all the little minutia that's required to tell a computer what to do. That's our real skill set as becoming programmers. It's slowing our mind down and figuring out how do we really solve problems. All right, so this guy shouldn't come as any surprise. 0 in our number system is just 0. Is 0 returns, well, it's kind of a cheat here, but you know it's true, right? Built into scheme is a predicate for 0 that returns true if the value you pass it is the number 0. False otherwise. Otherwise, we could just say the equal sign, whatever the value is in 0. They're synonyms. Successor is whatever the current guy is plus 1. Predecessor is the current guy minus 1. Straightforward. Okay. This isn't a weird numbering system for us, and this is the representation for it is pretty easy, certainly in scheme, because it's really that's how scheme is represented. This is almost a waste of time in scheme, except we're just giving ourselves this concept of a successor and a predecessor. And if we're solving problems in terms of that, that can be beneficial. And some of you maybe have seen, if you've worked in some of the newer languages, like, well, for example, what's the Apple language? Swift. Man, I tell you what, things are just I mean, they're just flowing out. It's ridiculous. In 2 weeks, I'm like an infant. So they're sucking. Well, I do that anyways, but sucking my thumb and yeah. In one of the things that I don't like about Swift is it's harder to manipulate strings in that language. And part of that is because the way they've implemented strings is a higher performance under the hood way of implementing strings. So getting a particular character in a place in a string requires you to kind of work with these things called indexes, and whether it's in strings or whether it's in arrays. And to get to the next index, you get the successor. So you have to do index-based math in order to get there. You can't just say, go to bucket 4. You have to go to bucket 0, then go to bucket 1, then go to bucket 2, then go to bucket 3, then go to bucket 4 by calling the same function over and over again or doing index math, where it's basically syntactic sugar for calling the same function over and over again. And under the hood, that's actually a higher performance. Okay, so that's the scheme representation. Then we get to our big num representation, which this is the one where they don't give you the answer. The 4 functions. So this is what you'll be implementing for Wednesday. But in the big num representation, which we already talked about, what would 0 be in big num? Here's big num. If we assume that n is a certain value, so assume n is 16, what would the representation? We see 33 is a 1 in the ones place and a 2 in the 16's place, because it's base 16. So that's 16 times 2, which is 32, plus 1, which is 33. What would a 0 be in base 16? A who? Empty list. No. Explain why your answer is wrong. What would the 1 be in base 16?
Oh. 16 to 0 power.
16 to 0 power, which is 1. So it would be a list containing a 1. That's the number 1 in that, right? What's the number 2? A list containing a 2. What's the number 17?
Oh, it's 1 1.
1 1. 1 in the 16's place and 1 in the 1's place. Yep. Catch it on now? So what's a 0? Just a list containing a 0. We have a 0 in the 1's place. 0 times 1 is 0. Base 16 value of 0. Make sense? So, function number 1 for this guy, the 0 function will be a lambda that takes in nothing and returns the list containing a 0. Does that make sense? That clear to everybody? Okay. What if we're testing to see if a big integer or bidget, bidget. I like calling them bigots. It's just more controversial. So how do we check to see if a bigot is a 0? You just told me what a 0 looks like. Now, would a 0 look any different if n was 8? Huh. 0 is 0. If n is 8, we have 8 to the 0's place is the is the 1's place there. We have a 0 in that bucket. It was the 291st. If n was 291, which we lose our alphabetic representation for that, right? We don't have enough characters, but mathematically we can make it work. We do have those places, correct? And then we just have to find a secondary representation language to deal with things that are bigger than a certain value. Now, so 0 is always there. Now, if we're checking to see if a particular bigot is a 0, how will we do that? How do you recognize a 0 when you see one? You just told me that a 0 is a list containing exactly one element, and that one element is a 0. That's how we represent zeros in bigots. How do you test for that? How do you write a function that tests whether a value is a 0? This is just pathetic. Go ahead.
Would you take the card, or you would put the list in, so you take the card, check to see if that's 0, check to see if the footer contains anything.
Okay, how would we check to see if the footer contains anything?
Check if not, CDR.
Yep. So what does a 0 look like? A 0 is a list whose car is a 0 and whose footer is the empty list. Right? Easy. It's an and. Well, if you're looking at the empty list, that guy's not. But technically, the empty list is not a legal input for bidgets. Correct? That's. So if we make the assumption for this assignment, which isn't an unreasonable assumption, that they pass in what is truly a bidget, which means that the simplest bidget, if we want to say that, and this was actually only positive numbers. I believe they don't talk about a negative representation here. Read through that, but I'm pretty sure they don't. Even though it would work up here for negative representations, having a negative representation of a big num would become more, you'd have to have some way of representing the sign, which wouldn't be the end of the world, but beyond the scope of what they're asking you to do for the homework. The homework isn't a matter of, we're going to just reinvent the wheel here, but it's a matter of kind of exploring this. So if they pass in something that is a legal digit, we're going to say, okay, well, we know this guy by default's a list, and we know it's a list that contains something. So how do we know it's 0? It's 0 if its car is 0, car is equal to the number 0, and its cdr is null. Cdr is the empty list. Make sense? All right. So now the two interesting ones come in. Successor and predecessor. Successor says, here's a digit, and so if you can write it, you can make the initial assumption that n is 16 if you want, because somewhere you're going to have to define what n is for doing your math. It'll just be a given piece of information. It's not part of the representation. Like when I've given you conversion numbers, I've said, here's this number, and I'm telling you that number is in base 8, or I'm telling you that number is in base 16, that kind of stuff. So that n is 16 thing isn't part of your inputs. It's part of your given information. You're being told what that is. So I would encourage you, maybe when you're doing the homework, just assume n is 16. And it wouldn't matter. If you assumed n was 9, you would write the same code, right? Because this is a representation of it. The code's not going to change. Just whether or not you're multiplying by 16 or multiplying by 9 as you walk through the list is the only thing that changes. So how do you, if I give you a hexadecimal number and I tell you to add 1 to this, how do you do that? That's what you're going to have to consider for successor. If I give you a hexadecimal number and you have to subtract 1 from that, that's what you're going to have to consider for successor, or predecessor rather. That makes sense? So homework for Wednesday is, whatever it was, 2.1? 2.1, this guy right here. Sound good? And we already just verbally implemented the first 2 of the 4 functions. They were the 2 easy ones, but still, it's the first 2 of the 4. All right, I will see everybody on Wednesday.